Hello, everybody. Yeah, thanks a lot for the invitation. Today, I'm going to talk about something new that I've been working for a year and more than that. And I'll not say the name again. I'll directly dive into what we come across as some interesting concept in distributed system building. I'm using word interesting because some of them could be possibly known and have my pedigree and I'm not aware of. And I'll be happy to hear from you as we make progress or afterwards. But some of them I knew, I'm aware that it possibly new, and I'm excited to share towards building distributed systems differently. So I'm going to start with what one may call as third generation blockchains, which are the new blockchains came in last 2 to 3 years and continue to come, where the key thing that they aim for is minimize the latency and maximize the throughput. The aim there is to have latency which is maybe less than a second or maybe up to a few seconds at max, and throughput is going up to 1,000 transactions per second or even higher. We have seen really huge and significant records that are getting built in last few years. If I look at the blockchain in general, we could look at them as the three key things: transaction delivery, that means making sure the transaction reach the node that's supposed to execute that, ordering those transactions, and upon that, then executing those transactions. Most of the earlier systems, if we can recall, they were performing this transaction in order. You are going to first deliver the data, then order it, and then execute it. Okay. But actually, it is observed already by several projects. It is not necessary that we have to do this delivery and ordering in this order. Okay, the order for these things can change in general. And indeed, most of the recent systems follow approach where it is possible that as the system load increases, maybe we can order the transactions or batches or blocks of transaction faster as compared to when we actually deliver them to the appropriate nodes upon which they perform the execution. Okay, so recent SMR design do follow this bit of asynchrony here itself, and this is allowed and this is accurate and provide benefit towards making a faster progress as we can. However, we observe that the changing this order may not be enough. A question can be worth asking. We already see the division of ordering, delivery, ordering, and execution. Do we really need to perform all these three actions on all the nodes? Can we perform some of this action only on the few of the nodes and possibly try to gain scalability from that? So hold on with that question. That question is going to become more prominent as we make progress and we observe that we're using same systems now to solve problems beyond just plain running a coin or a SMR mechanism. Let's say we're using the same system in the Web3 or DeFi world to have oracles running on the same systems, or let's say we want to provide randomness service, automation network, to name the few prominent which have emerged in few years. And let's say I want to use the same set of node to perform more tasks. They are going to feel the burn because they are performing same task again. And basically that means we are performing, let's say, 3 of them plus SMR. So that means each node will be now performing 4 tasks and can significantly slow down, can happen because of that. And indeed, we can call that maybe in the future, if blockchains are used for multiple purposes, these nodes will be overwhelmed. And typically, how can we solve this overwhelming problem is that either we try to scale horizontally, that means we divide the task, and different set of nodes perform the different tasks. And that approach is certainly something that can help to deal with this overwhelming and scalability issue. But this can be more failure prone because we are keep on adding more nodes into the system and see that still my failure tolerance remains the same. So I have 100 nodes and 33 could have failed. And now 1,000 nodes and still 333 will fail. This way of building indeed say that the system at the higher level in particular should be able to tolerate more failures and not less. We could try to scale vertically, which means that add more hardware, add more networking support at the system. But obviously, we know there are limits to it. And actually, all these approaches can also become certainly significantly expensive because now we have to buy better and bigger machines. And that can become a barrier for entry if we want to have node operators which are not part of a permission system in general. So it can be not only cost barrier, but also can result into an entry barrier into the system like that. The question that we ask is that, can we do a better job with the same set of nodes? I already have a system working where I assume that I have 2/3 honest majority. I'm working in a partial synchrony / asynchronous world. So that's the reason I'm assuming 67% honest majority, can I do a better job by using the same set of nodes and improve the scalability of the system and handle more job together? And one of the key insights that we will start with our discussion is that ensuring transaction ordering before delivery can offer significant advantage. So that doesn't mean that the transaction delivery can never occur before, but we'll make sure that no need to ensure that, and we'll still perform ordering. And our aim is that to somehow use that to improve the scalability in terms of the nodes that we need in that respect. I'll right away jump into what we achieve, and then I'll explain how we move towards it. So the typical approach that we employ, if we take the task of transaction delivery or data dissemination problem, which is also, for example, those who are aware of Narwhal Tusk kind of work, they call it mempool problem. That problem, transaction typically employ some version of reliable broadcast protocol, which requires two-thirds honest majority. What we observe is that, in fact, assuming that we have this SMR, which is simultaneously we are trying to build, if we use that efficiently, we could solve that problem with only 51% honesty. Okay, so what happened because of that is now once we achieve it, and I'll go into how we solve it that problems very soon, we could be able to scale system much better, and that's the approach I'm going to call here. So I'm usually going to use some simple terms like Tryman plan. So we'll assume that we have a system where we have two-thirds honest majority, as it will be required any partial synchronous or asynchronous SMR systems. And that is going to solve the ordering problem. Okay, ordering means ordering the transactions. But important thing is, to order the transaction, it's not necessary that we have to know the transaction. It is perfectly, we can order the transaction just purely based on the hash of the data or some kind of a commitment / signature on this data. And once we solve this problem, all other problem I want to solve with 51% honest majority. And what will be the advantage is that if I'm willing to tolerate a small statistical error, now I could divide this set of my set of nodes into what I can call as clan, where each of these clan, except with a very small statistical error, like failure in 1 in 1,000 years kind of scenario, we will be able to solve the problem only with the 51% honest party. And the idea will be, in this example, just to illustrate, let's say I'm performing 4 tasks into my system, okay? And in this case, what could have happened is that I would have, in the traditional system, I would have run the SMR as well as the 4 tasks on each of the nodes in the stripe. So that means each node will have performed 5 tasks in total. Now, if I divide the system in this way and all of my 4 tasks can be solved with only honest majority, each node will have to run ordering service, but beyond that, they only have to run one more service. So in that respect, the load on the systems can significantly reduce. So that was the whole premise where we try to build. And my aim is to show that how interesting problems in the blockchain space could be solved in this particular manner. In fact, the key thing I want to demonstrate to this talk is these clans or small committees of only much smaller than the entire tribe or entire 3F+1 committees is pretty common across different synchronous and partial synchronous settings. So overall, what our approach will be, we will be running SMR or atomic broadcast protocol on the system, which we'll call a chain of integrity, because we will not be including data into such environment. Our whole premise there is to make sure that we have ordering of the data. So hash of the order is decided, but anything beyond that, we try to solve that problem separately. And that's the reason I call this as a chain of integrity. From the conceptual perspective, it's just a pure SMR problem. Or at least in the recent works, the way SMR looked at, or atomic broadcast problem. But I'll be just working on the hash of the data and not actual data. And then once this is done, then we run this ABC to achieve this, no data flow through this environment. And then my aim will be to show there are very interesting and relevant problems that we can solve in such clans. The first thing will be obviously the data delivery problem that I already mentioned. We can, in fact, it is already known and work by Lindgren and others already observed that executions can indeed be performed again with only 2F+1 parties, so can work in this clan environment. what we observe interestingly is that there are versions, I'm going to use this word, versions of distributed cryptography and MPC that can also get solved into this clan system, assuming access to an SMR. And so is the distributed oracle or Byzantine agreement kind of a problem. I want to importantly emphasize here for those who work on cryptography that this is not a broadcast channel assumption. I also add a slide just to be sure. So typically in a broadcast channel assumption that's employed in cryptography, we assume that there's a fixed delta. And if you do not hear a message from a party in this time delta, you know that that's one of the malicious parties. We can't expect that to hold in the synchronous or partial synchronous system. So here the guarantees are very similar or purely similar to the state machine replication or atomic broadcast guarantees that we assume, that eventual guarantee in terms of adding transaction as well as when they will be visible to different parties. So message view for the receiver view, they're all, they have a prefix order, but beyond that, there is nothing else that we can guarantee. And that provides a significant difference. In fact, I'll be at least allude to some of the cases where problems are easily solvable in clan for broadcast channel, but cannot get solved when we assume this chain of integrity or SMR channel. And the final thing is, once we assume access to SMR, it could be solved either in partial synchrony or asynchrony, wherever we want to solve. Once they solve, the aim here will be to build rest of the primitive on top of that, all the things I'm showing here, in a purely asynchronous manner. That means the messages can be delayed. For any order that is message delivery is completely under adversarial control. And so is once it is added to the SMR or added to the system, the visibility of that to the system will follow prefix order, but still completely asynchronous beyond that. So now with this background, I want to give an example of the two protocols in this space. And I'll leave with several interesting directions to be considered in the end. So protocol design using chain of integrity. So I'm going to start with the this data dissemination or data delivery problem, where this problem has close similarities or equivalence in some scenarios to the reliable broadcast problem that is well studied in the distributed computing literature. I'm not going through the technical definition. I just put here as a representative. But the reliable broadcast idea is that sender want to send some message and the rest of the party should get it in a reliable fashion, such that if any two parties get the data, they get the exact same data. And if one honest party gets data, other will eventually get the data, kind of a guarantees. These are just formalism for such reliable broadcast guarantees, where I separate out the liveness and safety property, because that was helpful for building what I wanted to build. Okay, but I'll be happy to discuss the technical details with others, but moving on. And it is known that for this system, there are very interesting works that have happened. I'm just going to state the oldest or most prominent is this Brakha broadcast protocol. And it typically follows these three phases of send, echo, and commit or output kind of protocols. And the key thing to note here is that this problem can be solved only for n greater than 3f. So that means 67% honest majority is required, which is the lower bound is also provable even when you use signatures or other mechanisms. Now what I'm going to introduce is an abstraction, which I'll then justify is solvable by the chain of integrity. And that abstraction I'm going to call as an arbiter. So what does arbiter do is that an arbiter declares a particular payload to be certified by the arbiter if arbiter is sure that at least one correct node already has accepted it or already got M value to themselves, okay? That doesn't need to be the proposal. It can be anybody, but arbiter knows that at least one honest party has this particular value. Just to add more detail to the arbiter, that again, important thing is that arbiter doesn't need to know the message. It can just work with some kind of a hash of the message with the constant size bandwidth and independent of the message size. And it only aims to offer integrity. It knows that I don't know the message, but I know that at least one honest party had this message. This can be realized using any asynchronous broadcast protocol or SMR. I'm using the terms because in the literature recently, we do use these things quite interchangeably. So ABC, like atomic broadcast protocols or the SMR, they all can provide it. I'm going to they are sufficient but not necessary to some extent. And the idea will be, given that, the problem becomes interesting to define is because we want to allow multiple instances of reliable broadcast working simultaneously. And as some of you in the audience might already know, that although reliable broadcast primitive is a purely asynchronous primitive, the moment we add multiple instances of that, there could be memory bound issues that can happen for when we run these such systems simultaneously for multiple rounds. And to resolve with that, we have to deal with the more nuances in the definition. So we define our delivery and our output, suggesting that our output means the session has ended, and our deliveries are the message that continuously keep on getting disseminated, and we know that there is already information available to all honest parties in the system. And with that, again, I'm providing definition. Again, I won't be able to go through the definition, but I'll be happy to discuss definition, as well as happy to share the paper, those who are interested to look into that more. But the protocol is easy to understand. And unlike David did, I removed arrows, although it's a cryptography protocol. So the important thing to observe here is that I'm not working with 4 nodes, I'm just working with 3 nodes. So 2F+1 system. So the idea will be there'll be leader or the batch or the message proposer in the system who is going to send the message to other participants in the system, including itself, I added. And they are supposed to sign this message, and either threshold signature or multi-signature either works, and send that information, let's say, back to the proposer. And what this signature says that, first of all, it's an asynchronous system. So although I'm showing that everybody is sending back the message, it can very well happen that F of them, or one of them in this case, do not send the message. So they have to tolerate n minus f of those message. But if we want that this either multi-signature or threshold signature to be a sufficient guarantee of the data availability of at least one honest node, that will inherently require 2F+1 here. And in fact, we prove that that is necessary and sufficient. And once this is done, now such a certificate can be sent to these arbiter, or in our case, the chain of integrity / the SMR or ABC channel. And that way, we now have approval that this is the message which is getting certified by arbiters or this SMR protocol. We know that at least one honest party has this message. So it is always possible to recover the message from that honest party if the proposer is malicious and only sent to some honest party, but not. But we know that the message is recovered, and we can continue to use that and employ such a thing for data dissemination or delivery. Okay, so that was the key premise. Before moving on to another example I want to give, I did not go into the execution part of it, but as it is clear, once the data is ordered and we only perform this data dissemination in such a clan or a subcommittee of node, execution can also just perform in the subcommittee of node. Execution is already, once the ordering is done, execution for the rest of the system is a purely problem. There is no equivocation that can happen and can be solved by purely 2F+1 system. And I'm not going into detail there. I want to use rest of my time to go through yet another sitting, which we can call as a distributed oracle agreement problem, DORA. So where the idea is that now we need access to oracle. So the idea there is that most of the blockchains or smart contract are isolated from the rest of the world. And when they want access to the outside information for their smart contract or other purposes, they cannot directly get that. And that's where the Oracle networks come in picture, where these Oracle network systems collect the data from the outside the world and provide copy of that data to the blockchain, which can be accessed via smart contract or other mechanism. Typically, the idea for such organization could be there could be different data providers where the Oracle node collect the data from, and then after that, they have to perform some kind of agreement and find out the things from there. We want to make sure that this data gathering is happening in such a fashion that it's not, it can tolerate bad behavior by some data sources, as well as some of the nodes that are collecting the data. So every data source is collected to multiple nodes, and every node is collected to multiple data source. Kind of a thing will be necessary. And that's an interesting thing, but let me move on and again focus on distributed systems problem. Let's say we already solved that problem. Now we have Oracle nodes, and each of one has the data, and we made sure that honest parties have honest inputs available in general. And in such a scenario, we still need to solve that Oracle agreement problem. where we want to make sure that indeed they agree on something. And most interesting thing is that everybody is going to provide input and they want to agree on the value. And the typical expected thing there is what we call as min-max validity, which means that we want to make sure the final output is between the input and output, the basically input range of honest parties. So honest minimum and honest maximum, and your final output will be somewhere between this. And this problem is very similar to or almost equivalent to the Byzantine agreement problem, which is studied in the distributed system work for several years. And also the approximate version of that, where the min-max validity is more closer to that. But again, this required 67% there. My aim here will be now to show how can we solve this problem using this chain of integrity mechanism I'm employing. For simplicity, I'm assuming that I'm also putting data for here, but you can assume that there is a XRBC sitting in between that data destination channel I saw and to solve the problem. But here you just assume, I think they're posting data directly. This is a problem where there's every node is providing some input, and some of them could be dishonest and others could be honest. And we want to make sure that the value is in the range of these honest nodes. And to make it work, that it's in the honest range, one of the honest input, this M4 is never reaching the system in time, and they have to make the decision. And to make sure that the value is in the correct range, there should be honest majority among the input that are considered. And that's the reason such a system, by definition, required 3f+1, even when we assume SMR channel. So what are we doing here? So indeed, such a system still required 3f+1. But what this system allows us to think in deeper that why is this happening? And what we observe that in the real world data, it may be situation that the honest inputs could be in a range. They can follow a pattern. Let's say, and there could be multiple patterns. I'm taking the most simple example. The most simple example could be that honest input from a coherent cluster with the, let's say, distance delta. So all those values will be in the distance delta. And now question that we ask that can we solve this problem more efficiently? And what we say is that we reduce the increase the range of possible values, but we observe that the problem can be indeed solved now with the clan with 2f+1 party. So as I'm showing here example, if the adversary input is in the range, that's good. We'll use it and solve the problem. If it is not in the range, we are going to throw it out and take the two honest inputs and make the progress. So that's the way it allows us to go from 3f+1 to only 2f+1 for such a system. And again, because of that, we can scale much better, because now rather than each of the node working on every data pair, every Oracle problem, they can divide the work. And important thing I want to mention here is that as the system grow, we'll be able to divide even further better. I mean, the example I'm giving maybe work for 200 nodes, something like that. But let's say if I have 1,000 nodes, I will be able to form 1,000 clans, just to give, by maintaining the same statistical error. And by my error will be defined failure in one in maybe 500 years or 1,000 years. So, but it can happen that such a system is not followed, and it's still very easy to have a fallback where we just solve the problem now in the entire tribe. And we observe that for exchange data that we consider, that happens only maybe one in the 1,000 cases that we have to go from the clan problem to the tribe problem. Okay, this paper is already published, and I'll be happy to give the reference, or you can just search for me and you'll find it. So, and in that case, we'll solve the problem for 3f+1. Okay, so what we observe in terms of summarizing my talk is that we observe that there could be many interesting primitives in distributed systems world, which can be solved if possibly for only tolerating up to 49% bad nodes by having access to such a system. We looked at the example for the Oracle problem and the data delivery, but other things can also fall in similar boundary. And just to add on, there could be multiple benefits of that. We believe that this approach can allow us to solve the asynchronous distributed computing problem more efficiently. And it can also allow us to bring the cryptographic protocols which are work for the broadcast channel models to apply them in the asynchronous or partial synchronous world efficiently, and as well as allow a modular design that tomorrow I want to change my SMR or ABC, I just change it and the rest of the system continue to function as it is. Okay, so do you have a minute? Okay, yeah. So very quickly, so there are many interesting things that we are looking into. One aspect could be there is a very interesting paper that appeared in CCR called Gearbox, which also apply similar statistical errors, but also apply them differently for safety and liveness, and such a systems can be even more efficiently can be applied in our setting for the clans in general. And we are looking into that. Making it work against adaptive adversary is also an interesting challenge because such a statistical system assumes that adversary has already fixed their node before I do the sampling. So we are working on that. And as well as we are looking generally how to use that for MPC compilers. But I want to indeed end with very interesting thing, right? So it's not that all problem can be solved in clan. So my aim is either solve the problem in clan or prove impossibility. And there are interesting examples. For example, if we take the like data availability primitive or data availability oracle kind of thing, and if you want to make sure that the size of the data remain constant there that is stored, it seems like it will be challenging in such an environment, just to put thoughts here. Or same thing can also happen for protocols such as asynchronous verifiable secret sharing, solve that problem. If you want unconditional hiding, seems at least whatever we have seen so far, it just looks that we are giving up on solving this problem in clan. And in general, defining the general characteristics of distributed protocol, which we can and cannot solve in this clan model, is generally interesting. And I'm very excited to explore that and determine those lower bounds and characters and structures. Okay, thank you.